morning, everybody. Thank you very much. Thank you, Bartosz. Thank you, all other organizers. It's my great pleasure to be here. In fact, the very first time in my life in London. Indeed, I was asked to tell you something about quantum entanglement and geometry. I will first start to discuss the very simple issue, the geometry of quantum states. So for one qubit, everybody knows what is the block sphere. Sphere like sphere, ball like ball. This is simple. For one qubit, we teach our students to know very well all pure states of one qubit correspond to a single point on the sphere. This is simple. But this issue gets more complicated if you discuss higher dimensional systems. Of course, to speak about entanglement, we need to go at least to number 4. Within the space of states of size 4 is not as simple, it's not a sphere, not a ball anymore. So, the sphere is simple. You all know by heart everything. This is just a state which corresponds to a given point at the sphere. So the set of pure states is just a sphere. From a mathematical point of view, it's complex projective space CP1, but it's just a sphere. So you can, for instance, parameterize any point like this using geographical coordinates like theta and phi correspond in geography to latitude and longitude at the globe. Therefore, the word geometry can be used somehow directly. It's like geo, like our Earth. For higher dimension, it's not about the sphere. This first point. For qubit is a sphere. Later, it is later. For higher n is CP, for instance. If n is equal to 3, it will be CP2, so complex projective space of size 2, which has 2 times 2, 4 real dimensions. It's not a sphere anymore. We don't understand, at least I don't understand the geometry of complex projective space so well, mathematicians do, but we only need to know that this kind of, in some sense, it's similar to a sphere because it's kind of isotropic manifold. There are no distinguished points. Like, you have a sphere, and so far no points are distinguished. And this is very nice continuous manifold, but it has to be embedded in high dimensional space. Now, a simple concept, if you have two states, is distance between them, and the simplest possible distance somehow is always related to the overlap. You can take scalar product, absolute value of square, on the absolute value, take any reasonable function. One possible function is just arc cosine of this overlap. This is called sometimes Fourier study distance between two pure states. Of course, this works for states of arbitrary size. And then look, what is the standard unitary evolution? It's very simple. We take a vector, our state, and we just rotate it. So the unitary evolution is simple. It's just a rotation. If you take a qubit, it's just in fact rotation in our three-dimensional space, because block spheres embedded in R3. For higher dimension, it's rotation in higher dimensional space, but it's still rotation. And rotation, what kind of transformation it is? It is an isometry. If you take two states, like here, and rotate them, the distance between them, this angle, will always remain fixed. So, well, we see that if you have any Hamiltonian, you generate unitary evolution, so you can transform state into psi prime. And of course, scalar product is preserved, so any unitary evolution is isometry. So always the distance between two pure states under the any unitary evolution is fixed. Right? There's a kind of a catch here, because of course you know that classically there are also non-regular, there exist models of counting dynamics where any 2 points diverge in the base case. So here's a catch, because here you see that in quantum mechanics basically any unitary evolution is isometry, distance does not change. So what happens for classical cases more or less large n, and the catch is because the limits t to infinity and n to infinity do not commute. This is somehow the field of quantum chaos. I'm not going to discuss any longer today, but somehow the important point is that those limits, time to infinity and size of Hilbert space to infinity do not commute. Let me go now to the case of mixed states. You know the definition very well. We take this projector onto a pure state. We take convex combination of projectors. This is our state law. Of course, those AI, they form a probability vector, so they are non-negative and some unity. And in a more abstract way, you can define the set of all mixed states, a set of operators which act on n-dimensional Hilbert space, and they are emission, positive, and normalized. So in the case of n equal 2, we have just nothing else as the Bloch ball, which is a convex hull of Bloch sphere. Bloch sphere contains all pure states, and its convex hull, so everything which is inside forms a rigid ball. It's just a set of quantum states for size n equal 2. So look, what is the dimensionality of this set Mn? Again, there are Hermitian matrices. So in general, if you have complex matrices, you have 2n square parameters. But because they are Hermitian, you have n square parameters. But because there is a trace 1 condition, you have to subtract 1. So the total dimension is n square minus 1. In the case of n equal 2, it's just 2 square minus 1 is 3. This is 1. But for instance, let's take n equal 3. 3 square minus 1 is already 8. So look, in the simplest non-trivial case, if you take n equal 3, so a cube treat in our stack, the set of mixed states is already how many? 8 dimensional. So therefore, look, for qubit I can show you how the set looks like. For n equal 3, I'm not allowed to bring with me to Britain 8-dimensional sets. I was checked at the airport. But look, there's one strange thing. There's an 8-dimensional object. It has how many? 7-dimensional surface. Of course, the boundary is 7-dimensional. But the set of extreme points, they are exactly our pure states, is only our CP2, which has 4 real dimensions. So it's a bit strange. There's a 4-dimensional connected component of pure states, which sits inside 7-dimensional boundary. Okay, to be honest, it's not so simple to analyze everything, but we can try at least to have a kind of a vague understanding of the function. One more issue. If you have a qubit, so we know what is qubit. It's just up state or down. So the set of pure states, classical, there are only 2 points, 0 or 1. Set of classical mixed states is a convex hull of 2 points, which is just entire segment, because you have a probabilistic mixture of 2 points. So this is the set of classical states. If you want to quantize it, this is in a sense simple. Quantization looks like this. Now you get already what? You embed the set of pure states, the classical states inside of the set of mixed states. So you see this is the Bloch sphere of pure states and Bloch ball inside. So this is kind of a quantization procedure. By the way, you know what is this? It's a decoherence. Because you get again the set of classical states. So this is simple for a qubit. Now, for a Q3, how looks a set of classical states from n equal 3? There are 3 points, 1, 2, 3, which the distance is the same. So of course they form a nice triangle. And the convex, so there are 3 pure states, classical, and the set of classical mixed states is just a triangle. Now, to quantize it, I should take kind of a balloon and blow it to 8 dimensions. I cannot do it. So this set, this object I'm trying to investigate, of course it will contain inside this triangle of classical states. So I want to understand the properties of the set of mixed states, which is 8-dimensional. It contains, for instance, such a triangle inside. And then it has 7-dimensional boundary, and the set of extremals of pure states only 4th dimension. Well, so, in a sense, if somebody asks me how this set looks like, I can tell you, I don't know. Well, I was studying this subject for 20 years, and then I can tell you, well, I don't know exactly how it looks like, because I'm still not able to work at 8 dimensions. Maybe other people are, but it's not so simple. However, do you know the word apophatic? What means an apophatic approach? This is the way if you at least know how this set does not look like. This I can tell you. I know how this set does not look like. For instance, let's look at some pictures. For instance, this is a simple picture. And you please tell me, if this is a good couple look like this, yes, why is a model how our set does not look like? So, why our set is not like this? Why? Sorry? It's not convex, yes? It's a non-convex set. So again, now I'm showing you how this set does not look like. Yeah, is it clear? We know that this is not the model. So this is a good model how the set does not look like. This is the advanced approach. Okay, this is a tennis ball. So we know for n equal 2 it was a ball. For n equal 3 we know it's not a ball. So again, it's an example how the set does not look like. Okay, so here are our apples. So again, why our set does not look like this? Who knows?
Nothing maybe.
It's not a polyhedra, it's not a polygon. This is still a polygon. This eight-dimensional object we know is certainly not a sphere, neither a sphere nor a polygon. It has some round parts and some faces. What about this? Look, this is just a standard cylinder, but it's better in a sense because it contains some flat parts and some round parts. So it's a little bit better model, but according to this approach, it's still a model how the set does not look like. So what is missing here? Why this is a model how the set does not look like? If you don't know the answer, please have a look. Here something is in red. Here, it's a circle. Okay, this is how it looks like. One circle here, one circle there. You know how a cylinder looks like. So what is wrong? Why is a model how the set of mixed states does not look like? Please wake up. We are after breakfast. You don't know. Sorry? Yes, okay, but this is more sophisticated, yes, but now I'm talking about pure states. Look, the set of extremal states, to make a cylinder, you need what? You need to take one circle here, one circle there. So what is the set of extremal points for the cylinder? Two circles, yes, you don't see it? Okay, circle here, and circle there, take convex hull, you get a cylinder. So there's nothing wrong with it. What is wrong?
It's not connected.
Yeah, exactly. The set of pure states here consists of two separate rings, two separate circles that is not connected. And we know that in quantum mechanics we can go from one state to another in a continuous connected way. So this is again model how the set does not look like, but please have a look here what I did. I made such a rotation. Now please have a look at this object. It's passed over, it's a bit more fancy. This is now a simple trick, but now look, now I managed to repair this disadvantage because now the set of pure states is already connected, yes? Are you with me? So, but again, it's not a perfect model. But now here, you have a model. You should put inside a triangle, kind of, its cross-section should contain a triangle, which is here not the case. By the way, if you take the tennis ball and take the convex hull of its seam, it will just produce such an object. You can cut away something. By the way, you can cut away almost 50%. So this is the model again. This is now the sphere, and this is somehow this object, which is just a convex hull of such two twisted rings, and basically it's strange to realize it contains only a bit more than 50% of the entire sphere. So it's a bit better model, but still not perfect. So this was, by the way, another issue. You can take a triangle like this and rotate it in a clever way and take convex hull of it. So this is already a bit better because it contains a triangle. It's already a three-dimensional model, but it's always not easy to find for any object like this some properties of the set of mixed states it does not possess. Basically, it's not eight-dimensional. This is simple. Well, so this was kind of, in a sense, negative, apophatic approach. I would like to at least understand how the set does not look like. Now, if you really want to understand something better, and you insist to understand something about this set, if it's 7, 8, or 15 dimensional, what you can do? Not much. But always if you have a set, you can first look at its cross-sections or projections. Let's assume you have an object. I'm not seeing here, okay? There is a shadow. Sorry. There is always a shadow of an object, and you can somehow visualize. You have a three-dimensional object, you can look at its shadow at the two-dimensional plane. But also here you can do the following. You can take eight-dimensional object, which is somehow here flying around there, and you can project it down to, let's say, two-dimensional plane or three-dimensional space, and look how the projections look like. And then, okay, you will not, of course, understand everything. But in a sense, like in quantum, in the classical tomography, having a lot of cross-sections, you can somehow figure out how the object looks like. Of course, if you go from 8 to 2 dimensions, you will lose a lot. So, there is something in operator theory, in mathematics, a notion which is called numerical range. It's a kind of mathematical notion. Physicists are usually not taught about it, but it has a very simple physical interpretation I will tell you about. So basically, the same strategy works later to study what we are interested in, the space of entangled or separable states. It's also a subset of this main dimensional set. You now can look at its projections on a screen to understand how it really looks like. So let me go with the simple definition, which you, in a sense, implicitly you know. For any operator A is any operator acting on 8-dimensional Hilbert space. The numerical range, in German it was a very good formula that is always often denoted by W. It's, look, the set of all expectation values. In our language, we have operator A. If this is Hermitian operator, there are expectation values among all pure states which are normalized. So this numerical range is set of all possible expectation values. So simple as that, among normalized states. Why it is called the range? For a Hermitian operator, of course, the spectrum belongs to the real line. If, for instance, there is a matrix of size 4, it will have 4 eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4. Of course, they can coincide. It is very simple to show that this numerical range is just the range from this smallest to the largest eigenvalue, and it gives us the interval in which all expectation values have to belong. So it's a set of possible expectation values. From the smallest to the largest eigenvalue before the word range. So this is the numerical range for any operator. Something like 100 years ago, an important theorem was proven by Hausdorff and Teplitz that the set is complex. It's always a complex subset of the complex plane. In general, for non-Hermitian A, it could be a complex set. It's always a complex set. And for a normal matrix, by the way, do you recall what the normal matrix? Normal matrix is simple. If you have a matrix A and it commutes with its adjoint, if this is fulfilled, this matrix here is called normal. Which is, of course, the case for any Hermitian and unitary matrix. So for any normal matrix, there is a very nice theorem that this set is just a complex car of eigenvalues. In principle, we can have a complex eigenvalue. So one, for instance, this is kind of a random normal matrix of size 6. You have 1, 2, 3, 4, 5, 6 points. They denote eigenvalues. And it's just a complex car. It will be always a polygon. In this case, it would be a polygon with 5 sides. If you have a generator from not normal matrices, which do not satisfy this relation, then always eigenvalues belong to this set, but set is a bit larger. And then this boundary is already, it's not a polygon, it's differential. Well, in the case of n equal 2, the situation is very simple. If you have a normal matrix with spectrum lambda 1, lambda 2, then the numerical range is just interval from first to second eigenvalue. For any matrix of size 3, you have 3 eigenvalues. Generally, they are distinct, and again, numerical range is just a complex car of 3 points, which is just a term. This is the proof. By the way, if you have any questions, something is not clear, so please, yes, wait.
How do you generate random normal matrix?
No, okay, this is a very good question. I will please discuss it this afternoon. No, okay, on the time, because, okay, it is not, but thank you for asking me this. I will discuss it a bit. Yeah, good one. I don't want to go into details here, but this is only a side remark. Now look, what happens if you take a non-normal matrix? By the way, what is the most famous non-normal matrix, simplest non-normal matrix, which you even cannot diagonalize? You know any? The one of Jordan, J. It is 0, 1, 0, 0. Have you seen such a matrix in your life? Well, mathematics. But it's not normal. It's very much not normal. Why? It's non-symmetric. In a sense, it's as non-symmetric as it could be. Yes, you see non matrix. In quantum mechanics, we usually don't care about it because we don't use it very often. But of course, in mathematics, it exists and it's important. So, in general, the statement is that for any normal matrix, this numerical range is closed to T1, while in the general non-normal case, it's an elliptic disk, and two eigenvalues are focal points. This is like 90 years old or something like this. So, for the Jordan matrix, by the way, what is the spectrum of this matrix? Who knows? 0, 0, yes, it's clear, you don't need to count much. 0, 0, so basically there are two focal points, they are the same, so just this. So in the simplest case, for the Jordan matrix, numerical range is a disk. Very nice, so circle, but full circle, like this. And now look, if you take this set of pure states, so this is a set of pure states of size 2, and ask, you take a sphere, and ask, what are the projections of this sphere? No, you will not see it. No, usually I get a projector which was projecting, so basically you can guess that the image of a sphere is always this. So you can ask, what is a relation between those numerical ranges and the projection of the set of pure or mixed states on the plane? And there is a relation which was known in the literature for some years, but I think we somehow emphasize it recently more directly. Here are again just those projections, the numerical ranges for a circle or an ellipse, and then just they correspond in a sense to shadows. If you take the three-dimensional object and look at the shadows at the screen, two-dimensional screen, okay, here you can also talk about probability measure. They are not the same measures. But basically, the idea is that you have higher dimensional objects, and you look how their projections on the screen look like. So the key point is the following statement. If you have classical states and normal matrices, the relation is following. You take the set of classical states, it's just a simplex. So like triangle or tetrahedron, embedded in R to power n minus 1. That projections of this simplex onto a plane form up to a rescaling and rotation all possible numerical ranges of size n. For n equal 2, it was simple because all possible numerical ranges are disks which can degenerate to an integral. And this is so because if you take a set of states and analyze projections, it's always, or it is a disk, but if you tilt the screen, you will get what? An ellipse, yes? Let's imagine the light comes from you. If you tilt the screen, you will have an ellipse here. Yes? The projection will be an ellipse. For quantum states, the situation is even more interesting. Basically, if we take our object, so Mn belongs to a set of quantum states of size n, which is embedded, we know, in R to power n squared minus 1. For instance, M3 is embedded in R to power 8. And we study standard Euclidean geometry, so flat matrix. And now the point is the following. This set of orthogonal projections of this set of states onto a two-plane is equivalent to the set of all possible numerical ranges of all matrices of order n. So, to analyze projections of the set we are asking about containing all mixed states of size 3, you have to analyze all possible numerical ranges of all matrices of size 3. Well, okay, this is just to mark a short break, change of topic. This is the picture from Karol, where I and some of our colleagues here stay and work. This is the vowel custom at the display, which is a little bit larger than Karol than you're working with. A little bit. So, this is the Thomas picture. There are now 4 different classes of numerical ranges of matrices of size 3. So one is the triangle. It has 4 flat parts. Here is a convex hull of a point and an ellipse, which has 2 flat parts. Here is such a convex hull of such a cardioid. It has 1 flat part. And generally case just an oval. So those green dots denote simply eigenvalues of this matrix. So this was known somehow in the operator theory. Mathematics knew about it. But what is a little bit important for us, that those 4 classes, they form what? Are you with me? They answer to some extent our question. How the set of mixed states looks like? Why? They've shown all 4 classes of numerical ranges of size 3. So possible projections of this unexplored set on the plane. So we, know that the projections can look like this, or like this, or like this, or like this. Of course, it has to contain a circle in particular case, and a triangle in particular case. So there are projections of this 8-dimensional space onto a 2-plane. So now we skip there. This is exactly somehow classified how those projections may look like. It was done not so many years ago in 1997. But now look. This question of numerical range can be also considered a more general case. If you take not one matrix, but take, let's say, M matrices, and do the following. Physically, it corresponds to a joint measurement. If you have M observables, let's assume they are Hermitian, and you have a state, and you, for instance, measure Jx, Jy, or Jx, Jy, Jz. You make many measurements. You have many copies of the same state. And you make first measurement, second measurement, third measurement, and so on. And you can ask the results of those measurements of different observables produce a vector of M components. So you can ask, what is the set of all possible outcomes of those measurements? I only discuss expectation values. So if you take M equal to, any matrix can be decomposed into Hermitian and anti-Hermitian part. So then standard numerical range is nothing else as this joint numerical range of Hermitian, anti-Hermitian part. So now the point is simple. If you take M arbitrary, this joint numerical range of M different matrices forms a projection of our set of all mixed states. Here should be Mn. This is again the set of all mixed states into a not plane but space. R to power, for instance, 2 or 3, 3 is still 12. For instance, if you take n equal to, so 1 cubic states, and as a observables you choose familiar Pauli matrices. So you can ask, what is the set of all possible outcomes of measurements of 3 components of operator, angular moment operator? And what is the answer? Of course, just the standard sphere, because we know that if you measure Jx, Jy, Jz, and the original state is pure, we will get somewhere a point at the sphere. If you take mixed states, it will be inside the block ball. If you take for n equal 3 set of all Gell-Mann matrices, they are generators of the good SU3, there are 8 of them. Usually they are also denoted by lambdas. Then the numerical range, so basically the set of all possible measurement outcomes, if you measure those Gell-Mann matrices, will form exactly in 8 dimensions, will form the set of mixed states of size 3. So look, here, this is a concrete example of numerical ranges, now 3-dimensional. We choose any 3 matrices of size 3 and look for joint numerical ranges of those matrices, but physically it means we perform 3 measurements and want to see how those objects look like. So here I have a collection for you to show, but then this will be, so please some of those. Okay, here is the collection contains exactly 10 mistakes, some of those. But don't lose them because they will be necessary this afternoon. So you will see in a second why. And now look, please have a look at some of them. And what you can see, okay, each of them is important.
And this 3D printed.
Sorry?
This 3D printed. And this 3D printed.
Sure, okay, you'll see. Yeah, so how could we do it? So how to obtain such objects? Again, what it means? This is a set of possible outcomes of triple measurements for a Q-tip. So to obtain such a nice result like this, all what you need is a good student who is here. So Konrad will tell you, this is the printer you ask. So he knows this is the ink, this is the interface and the data here. So he will tell you all details about this during his poster this afternoon. So he knows everything about the production of objects and about their meanings. But the meaning is simple. What is the meaning? It's the projection of a dimensional object into a free plane. And he knows how to classify all those possible shapes. This is still for a Q-tip. To go to entanglement, I will have to go to animal form, which Konrad has not done so far, as far as I know. Anyway, he will tell you that you can divide all those shapes. They are different colors, and they differ with respect to number of flat faces and number of segments inside the boundary. So please go to his poster this afternoon. Here's again a picture of castle in Karol and the Vistula. There's also a boat, which goes up and down, or maybe the yes. But I enjoyed yesterday's event very much. So something more what you can say in general about the geometry, still about the geometry of the set of quantum states. This object is a ball for n equal 2. For n equal for larger n, it's not a ball, but it of course can be inscribed in the outer ball of such radius, and there is a ball inscribed in it, kind of called in sphere and out sphere, of radius capital Rn is the larger radius, and Rn is the smaller radius of the ball you can squeeze inside. So it always contains a non-zero volume inside. And then you can compute the volumes, and for n equal to, of course, the outer sphere coincides with the inner sphere because you have exactly a ball. It is possible, it's not so complicated or so easy either, to get analytical results for the volume of this set for arbitrary n. It's analytical result expressed with gamma function, or the gamma function. You can also compute the area of this set. So the set has dimensions n squared minus 1, boundary n squared minus 2. It's again a kind of not very difficult formula like this. But what is somehow impressive? If you compare those two results, they are very similar somehow. If you look at the ratio A over V, A is area, V is a volume. Somehow we want to compare area with a volume. But this would not be fair because dimensions would not agree. So it's better to multiply area with Rn. Rn is I call the radius of the insphere. Now the dimensions are the same. Area times radius has the dimension of volume. And you somehow divide, all those gammas go away, the result is n squared minus 1. Everything cancels out. But n squared minus 1 is what? What is the meaning of it? N is the size of the Hilbert space. We have in our study Q mean. But n squared minus 1, it is just the dimension of the embedding space. You have to embed the object in R to power n squared minus 1. So D is now dimension of the space. So now look, now this is important. What it means that the ratio A over V, area over volume, times R is equal to D. Have you ever seen this formula? How old is this formula? How do you think? I mean, this formula is kind of complicated. But somehow the ratio is extremely simple. So I want to convince you it is more than how many 1,000 years? What is the oldest reference you ever quoted? 50 years, 100 years, 1,000 years? Yeah, any ideas? This is the formula of whom?
Euler?
Whom?
Euler maybe.
No, somewhere, yes? You take the base, multiply by height, and divide, okay, the standard cone is divided by 3. And generically, the volume of a cone RD is base times height over D. Simplification. D is number of dimensions. So it's a kind of generalized Archimedean formula for the volume of the cone. In our case, it will be D cone. N is the size of the Hilbert space, and D is n squared minus 1. So look, our object set of mixed states, it has this remarkable property that the volume is just equal to, okay, let's do it this way. The product of area of the surface times radius of the insphere over volume is equal to D. So in a sense, you can say like this. Well, you take cone, you put here another cone, another cone. If you glue all cones like this together, then there is the entire surface is obtained from bases. Can you imagine this? Then this formula will be always satisfied. And then this class of compact bodies is called a set with a constant height, because the height is constant, independently in what direction you choose. So here, this statement shows that our set of mixed quantum states we want to analyze has a constant height. So its relation between its area and volume is so simple as in the cone of Archimedes, and this is valid for any n, where D is just n squared minus 1. Yes, so I think I have to speed up a bit. Again, a picture from Karol. And now we have eventually to go to composed systems and entanglement. Okay, to have a composed systems, you need to have at least 2 objects, like spin here, spin there. So the minimal dimensionality is 4. 2 times 2 is 4. What I talked about now was 3. So then we have to go to animal 4. It seems a bit more complicated. But we want to distinguish. To speak about entanglement, first statement, you have physically to say, oh, this is object A, object B. This is entanglement with respect to a splitting of the entire physical system into 2 parts. Only this makes sense. So mathematically speaking, you have to say, well, we have a so-called tensor product structure. Our Hilbert space has a predefined tensor product structure HA times HB, and then of course we know that any state which is product is called separable, any other like a Bell state is called entangled. And to classify, quantify entanglement, you can for instance take a partial trace of the projector and compute its entropy, and this entropy of the reduced density matrix sigma is called entanglement entropy of the state. If state is separable, then this is also pure entropy 0. If the state is maximally entangled, then partial trace is maximally mixed. So entropy is maximal, in this case is a log of 2. So the more mixed partial trace, the more entangled initial pure state. So by the way, look, here's a kind of a concrete picture. It represents a cross-section of the space of pure states for size 4. And it is 3-dimensional cross-section. You have here, like states, say 0, 0, 0, 1, 1, 0, 1, 1. It's a tetrahedron. And now the colors represent different entanglement. Blue is separable, and the more left, the more entangled. So here is one entangled state, it's just the Bell state. Superposition of 0, 0, 1, 1. And here is another state, psi plus, superposition of 0, 1, 1, 0. So there are, in general, you know, 4 Bell states. There are 2 here, 2 are out of this space. Why? Because they have negative, they have minus signs. Here I took only with positive, real positive components. So now look, here those lines, they are in a sense iso-entanglement lines. They are lines of the states of the same entanglement. Here you have only 2 points representing maximal entangled states. However, they are joined in somehow other dimensions together. By the way, this is just sorry for that first advertisement, a cover story of our book, but now you understand what this picture shows. But you have an idea what is now this picture here. This so-called ruled surface. It's a nice surface, Of course, it's not flat, but it can be obtained by two families of straight lines. In fact, it's kind of hyperbolic, but it describes here the set of all separable states. So the separable states, they form those four lines here, and inside they form such a nice ruled surface. It will be important. So please mark this picture here. So somehow here there are separable states, and entangled states is just as far from this surface as possible. So this was simple for pure states, for mixed states. The definition of separable state is the following. It's just a convex combination of product states. So the definition is simple. It's a classical, those states have classical correlation, so they are not correlated or classically correlated. The definition is simple, but the key point is that it's not easy to answer the question if you see a density matrix, if it has such a decomposition or not. So this is a key problem, entanglement problem, separability problem, whether a given state has such a decomposition. So the question is, if you are given a density matrix law, can you find such a decomposition? Perhaps you know, the separability problem is solved in the simplest case of 2 times 2 and 2 times 3 problems, so-called positive partial transpose continuum. And for the case of 2 qubits, we know everything. This is simple. For instance, what we know, if you now consider the following picture, take set of mixed states of size 4, and you take only spectrum, eigenvalues. There are 4 numbers, real non-zero numbers which sum to unity, they form a simplex. What does that mean? So any corner of this tetrahedron forms a pure state, and maximally mixed state here is just in the center of this smaller ball. And you can ask, well, where the separable states in general will be located? Of course, at the corner you might have this pure state. It can be either entangled or separable. Of course, separable state also exists. However, if you take maximally mixed state, it's easy to show that all those states around maximally mixed state with spectrum, we have all eigenvalues very close together. They're almost similar to 1/4. Then all those states are separable. So the first punchline, if you go from the pure states to mixed states, the more a given state is mixed, the less likely it is that it is entangled. And if it's sufficiently mixed that the spectrum belongs to this maximal ball inscribed inside the tetrahedron, it's definitely separable. So in general, if you we like to work with pure states, we somehow are in a sense afraid of decoherence. We don't like usually decoherence. Decoherence brings pure states into mixed states, and then in general we lose entanglement. So here's another cross-section, in a sense. For this, for n equal 4, we have 2 qubits. So once again, the size of the matrix is 4. The size of the set of the body of mixed states has how many dimensions? Please wake up. Can you do calculation n squared minus 1? No, but it's important. What we are talking about? The object we are discussing, even for 2 qubits, has how many dimensions? 15, yes? N squared minus 1, 4 times 4 minus 1. So we have 15-dimensional object. We can only observe those projections from 15 to 2 or 15 to 3. Or to try to understand something. But look, we are working now to understand entanglement in the simplest case. You need to cope with 15-dimensional space, which is not so simple. Here, it's just a kind of cross-section of this object. Here you have maximally mixed state. Here you have, in a sense, all pure states. Now black denotes the degree of entanglement. This kind of entanglement of formation. So here are maximally entangled states. This is this ball of separable states. This length is just the boundary or separability boundary. And here, look, basically, this degree of entanglement can be also interpreted as the distance to the closest separable state. This state is as far as possible from the boundary or separability boundary. One more issue. In the case of 2 qubits, the situation is simple because there is so-called partial transpose criterion. So any set, any state which after after partial transpose is positive, is separable. Positive transpose, partial transpose means that 1 times T active on law that this is positive. So PPT means that so positive partial transpose, which says that if this is so, then and this goes in two directions, law is separable if n is equal to 2. If you have 2 times 2 law. This depends on the criteria. So look, what is it? Here we have a transpose, partial transpose, you transpose in only one subsystem. So this is kind of a reflection. Here you take 1 is the circle denotes the state of all states, and then another circle denotes the state after partial transpose. So in this case, the set of separable states is just intersection of the set of all states with its reflection. So basically, you make form such a set. And now here you can even compute the volume of this. Okay, you can estimate the volume of this set here and the area of the set, of the boundary of this set of PPT states. In short, PPT states, positive partial transpose for n equal 2 coincide with the set of separable states. Okay, I think I have to speed up a little bit. I will not touch about quantum operations now. But of course, you know what it is. So block ball for n equal 2, it's any operation which sends a ball inside the ball. Of course, if it's unitary, it's just a rotation of the ball. If it's non-unitary, then you can have a contraction. So it's a map from sphere inside the sphere. You can have a depolarizing channel which contracts the ball inside. So you usually describe it in the following way. This is the Klaus form. You sum over AI, and now you have AI here, AI double, just to preserve the property that is out state is Hermitian, and if those Klaus operators satisfy the following identity resolution, then the trace is also preserved. So such maps, which are they are called CPTP, completely positive trace preserving maps, they are called also quantum operations, and any quantum process can be mimicked like this. And here is equivalent form, which may be easier to understand physically. You take our state, our initial state, yes, and add ancilla. So we have environment, then you take unitary which couples them together, and take partial trace, and this is the, here this is the outcome. Extending the system, unitary action in the extended space and partial trace. And those two pictures are of course equivalent. So here, there is a kind of simple model of simple dynamics which acts on 2 qubits. So all those operators, Klaus operators are given by Pauli matrices, it's very simple. But here, what I want to show you, if you now look, here is time, here is entanglement. You can see how the entanglement changes in time, and there are many different possible scenarios you can observe. Or you can okay, so basically entanglement can disappear, or you can observe kind of revivals of entanglement, and sometimes it can immediately decay and stay constant. This was first discussed in our paper with Karol many years ago, but then it was in this paper by Yao and Emily, and they coined, they also cited this problem, and they coined the name of sudden death of entanglement. Sudden death means that there is entanglement goes to 0 and then stays flat forever. Doesn't reappear. Sometimes we can have a revival like this. And look, we understood it somehow, but not too well 15 years ago. But now, you see, what I want to emphasize is geometrical investigations are helpful to understand such effects. For instance, if you know now that here is the set of, it's a kind of sketch of all states. This is the set of separable states, which includes this ball of separable states. Then you have time evolution, which basically this somehow means it's kind of possible trajectories. So the green trajectory somehow represents the case of revivals of entanglement. Here is the positive entanglement, here is 0, here is again entanglement but smaller, and again. And silent death is very simple dynamics. It's decoherence is so far, it goes once inside the set of separable states and stays there forever. Now look, we had such a kind of understanding some 15 years ago. some sketchy understanding. And this is exactly our numerical range. This is the linear picture, there are linear results. This is just the, let's say, artist sketch. And here you can find such parameters. So here is a set of states. Now this is a trajectory. This here dashed color means set of separable states. In fact, the projection of this set. So now you can really understand that you should see that those geometric investigations help you to understand and interpret such results of practical interest, how the entanglement changes in time. So I think I have to conclude soon. First of all, I want to emphasize that it's good somehow to understand as much as you can the geometry of the set of mixed states. For n equal 2, this is simple. For n equal 3, it's already not as simple because it's an 8-dimensional set. But at least we can study projections and cross-sections of this set onto a 2-plane or 3-plane. And those projections mean that the physical limit. This is just a set of possible outcomes of multiple measurements. And this approach is also useful to study quantum entanglement and its dynamics. And for instance, it helps us to understand two different scenarios which may happen. The scenario of entanglement revivals and the scenario of entanglement sudden death. So I think there's still 1 minute, perhaps 3. So I will use last minute to make a short announcement. There is a postdoc position starting this year about the grant title is Uncertainty Relations in Quantum Entanglement. And then to apply, you have to solve the following question. One question is difficult, where this building is located, and second, easier, how it is related to quantum entanglement. This is simple. So how is it?
I know where it is.
Okay, so you are it's not what about quantum entanglement? You don't see any relation? No, those people, of course, they study quantum entanglement. It's easy. No. This is exactly those ruled surveys. This is set of all separable states, yes? So the quantum entanglement states are from here, and this is the manifold of states which are equally distant from this maximally entangled state. And now, so you see the comparison with those rules surveys. And the question, so you know what it is? Yes, you do? So the answer is simple. This is Roundabout. So this is a small station in Warsaw. Maybe not the best picture from Warsaw, but this is what it was entanglement. And indeed, this postdoc position will be over in Warsaw, and you can see the web page of Center for Theoretical Physics in Warsaw, where this is enforced. Yes, thank you very much.
For entangled systems, could we maybe study the quantum geometry of each of the systems of the subsystems maybe to make conclusions about the whole system?
Yes. So for instance, what we did, Conrad here, stand up. So what Conrad did is Conrad is here. Yes, he also looked at this 3D images of the set of separable states. So you have the set of all states, now the set of separable states, and you can somehow look how one projection is made into another projection. This is one. Second, of course, you can take a partial trace. But then, if you have a partial trace, you will somehow lose some information about the time. But of course, any lose of information is inevitable if you make a projection. Of course, projection always decreases number of information, but sometimes you can infer something by looking at such projections.
Any other questions? I was actually going to ask a question.
Yes.
Because you talked mostly about Euclids, for example, or I mean, that's what you're going to investigate mostly. But I was wondering if there are, for example, dimensions for which unusual or interesting things happen in my dimension, from the set of quantum states.
Yes, nice question. So, first unusual dimension is 4, because it's first number which is not prime. And you can speak about the time limit besides 4. Later, there are special numbers which are somehow related to number theory, and then we can discuss those objects like mutual and bias basis or SIG POVL, so symmetrically information copy POVL and so on. And then somehow here, the point is interesting, the answer for some questions related to finite dimensional geometry depend on the fact whether the dimension is prime or not prime, for instance. like there was no problem usually about basis open for n equals 6, because 6 is first number which is neither prime nor power of prime. So somehow, in some subtle questions, dimensionality plays a role. But this afternoon I will talk about the opposite case if n is very huge, and then define whether it's prime or not prime doesn't play a role.